People are incredibly good at identifying patterns in the world around them. The problem is we err in the direction of seeing patterns. When it comes to what we would call our false positive rate, it can get us into a bit of trouble. I find that this false positive rate in pattern recognition really pops up a lot with variables that change through time, like abstract concepts, things like prices. Eggs have been in the news a lot lately because the price of eggs is pretty high, and people want to find meaning. They want to know why the price of eggs is high. One idea that's been put forward is that federal spending is driving the price of eggs higher. I can kind of see the reasoning behind it. The federal government has some ability to control inflation through spending. If this is true, then federal spending could be driving inflation up across the board, and that could be driving the price of eggs up. So we would maybe expect that reducing federal spending could bring the price of eggs down. It's a really interesting idea, and it's worth interrogating a bit. So let's reframe this. Let's say the price of eggs is a random variable. The future value of eggs is something we don't know. It's going to take on some value in the future. For example, consider this train. The train can go left or right when it gets to this junction. We don't know if it's going to go left or right. But there it goes. It went left. That's great. Let's take it a step further. Let's say that the price of eggs has some mean value. And every year the price of eggs bounces around. It changes values, but always kind of bouncing around this mean. We could say the price of eggs isn't dependent on anything. Let's propose an alternate idea. Let's say that the price of eggs has a mean, but the mean is determined by federal spending. So there's still a random element, but we expect the eggs to bounce around some middle value that's determined by the federal spending. So now that we have these ideas, we need to test them. We can download publicly available data on egg prices quarterly going back almost 70 years. We can also obtain data on federal expenditures going back really far. The price of eggs is certainly going up. It bounces around kind of randomly for a really long time. It seems to depend on nothing. And then around 2005, the price of eggs starts to rise, reaching a really wild peak right around the time of the pandemic. Federal spending, in contrast, has just been rising gradually over decades. And then again, during the pandemic, wild change. At first glance, both of these variables are going up through time together. So maybe federal spending is controlling egg prices. It's feasible. We want to test this objectively, and for that, we're going to turn to the F-test. Okay. Let's say we've got some data set where we've got y variable and an x variable, and it looks something like this. I'm going to draw a second copy of it right here. Now, let's say that we think the y variable is not related to the x variable. It's just a constant, and then we've got our competing idea where the y variable is a function of our x variable. We can write these two ideas out as our null hypothesis, where y is just some constant, some random normal noise. Alternately, we've got y is a function of our x variable plus some noise. Now you can see these two variables, these two equations are pretty closely related. If this term here goes to 0, they're equivalent. So we're really testing the idea that this term exists at all. For each of these models, we could measure the distance between our data points and our proposed best fit lines. Each of these little distances we're going to call E, which is a residual. This is just equal to simulated minus observed. We could also compute the sum of square errors, which is the summation of the residuals squared. Now, in order to determine this best fit line, all we're going to do is minimize the sum of square errors. That's called ordinary least squares fitting. So once these two different models are established, we could compute the sum of square errors of our null hypothesis and the sum of square errors of our alternate hypothesis. From this, we can compute the F statistic. So what this big equation for F shows us is that right here up top, we've got the sum of square errors of our null model minus the sum of square errors of our alternate model. By definition, the error here must be bigger than this because this line can reduce down to this line if the slope term is 0. So this numerator must be bigger than 0. The bigger the difference, the bigger the F value. Down here, you're normalizing this by the parameters in the null model minus 1 minus the parameters in the alternate model minus 1. So if you're adding a ton more parameters to your alternate model to make it fit better, you're going to get penalized. So from all of this, we can compute the F statistic, and the F statistic is going to follow the F distribution, which looks something like that, or sometimes something like that. We're going to do a little experiment where we use Monte Carlo sampling to generate artificial data sets between federal expenditures and the price of eggs where they're not related. On the right-hand histogram, you can see we're empirically building the distribution of the F statistic. So this is what we'd expect the F statistic to be under the null hypothesis. It's mostly going to be close to 0, tons of values near 0. So what this tells us is that if we see a really large value of F, we can say there's a relationship. So this approach using the F-test, it makes certain assumptions about the data. First, it's assuming that our x and y variables are linearly related. This may or may not be true. The second thing, it's assuming that the residuals, the distance of the data points around our models, are normally distributed, meaning it follows like a bell curve. And it's assuming that those residuals are distributed with a constant variance, meaning the scatter of the data doesn't get bigger as you move along the x-axis. Another tricky assumption is that the residuals are independently distributed, or the data points underlying the residuals are independently distributed. With time series data, like the price of eggs or federal spending, this is really hard to accomplish. Let's plot our data and just see how it looks. At the low end, expenditures and the price of eggs do appear to be linearly related. As we get out to larger values though, maybe that trend still holds, maybe not. But really importantly, we can see that the variance kind of explodes at the high end. So we're immediately violating one of the assumptions of the F-test. So if we perform the F-test on the annual eggs and federal expenditures data that we have, we get an F-test statistic of 283, an extreme value. The p-value, which is the probability of observing an F value this large, assuming the null hypothesis is true, is something like 1 × 10⁻38. Incredibly improbable. So this result would suggest to us we can reject the null hypothesis and say that our alternate hypothesis was correct, that eggs are a linear function of federal expenditures. The problem is that this test came with all those assumptions. We had to assume that our residuals were normally distributed. We had to assume the relationship was linear. We had to assume that our residuals were not a function of our x variable. And just looking at the data set again, it seems like we might be in violation of those assumptions. So we need an alternate approach, and for that we're going to turn to Spearman's rank correlation. So let's assume we've got some XY data that has some weird relationship. It's definitely not linear, but it's what we would call monotonically related, meaning as x increases, y keeps increasing. So let's work with some fake xy data for the moment. We're going to translate these x and y variables into the rank of x and the rank of y instead. So smallest to biggest, the rank of dates is just a sequence, and the y variable, we're just going to sort them and figure out where each variable would land in the sorting. Now we're going to compute the difference between the ranks, so rank of y minus the rank of x. And then we're going to compute the rank squared. So on. Once we have this set up, we can compute our estimate of Spearman's ranked correlation as 1 minus 6 times the summation of our rank squared all over the number of XY pairings times number of data points squared minus 1. And once we have this estimate of the rank correlation, we can test the hypothesis that the rank correlation either equals 0 or it does not equal 0. And if we find that it's not 0, then that tells us that y might be a function of x. So with Spearman's rank correlation, we can see that we get a very significant result. We get a Spearman's rho of 0.86 and a p-value of 1 times 10 to the negative 54th. Incredibly significant. So without doubt, there is some relationship between these two variables. Now, there's a whole debate to be had about correlation is not causation. There very well could be another variable that impacts both of these in the similar way, causing them to exhibit a significant correlation. But for now, let's keep it simple. But what we haven't done yet is try and estimate the size or the magnitude of the relationship. So let's go back to our simple linear model. We're going to go with the simplest case possible and say these two variables are linearly related and accept all the assumptions that come with it. And we're going to use it to predict the expected change in the price of eggs from some change in federal spending. So let's take the proposed 2 trillion. If we reduce federal spending by 2 trillion, we would expect a reduction in the price of a dozen eggs of about 53 cents. So if you're spending $8 right now to buy eggs, and the federal budget is slashed by 2 trillion, you'd expect to be spending $7.50. Reductions in programs that support health, military security, scientific research, education, early childhood programs, disaster recovery, once all of those programs and their benefits are stripped away, we'll be paying 50 cents less for